all our second webinar, whether you are a Fiber to the Home Council MENA member or not. I want also to thank our members, Sterlite Technologies, for this great initiative to present 3 technical webinars with special matter experts from Sterlite through the Fiber to the Home Council MENA platform. This week, we have Bend Insensitive Fiber Improved Network Installation, Performance and Maintenance with Dr. Seldon Benjamin, the Principal Solution Architect, MIA Sterlite. Let me first introduce Dr. Seldon. Dr. Seldon is an industry expert and veteran in the field of connectivity solutions. With more than 25 years of experience in the field of telecom, he has contributed to the development of technologies to enable new applications of fiber optics in many areas, including FTTX. He has worked across the globe in geographies such as North America, Africa, and the Middle East. Dr. Benjamin is currently with Sterlite Technologies, where he is responsible for new products development and innovations in fiber, cable, and connectivity solutions that provide an advantage in the deployment of fiber optic networks. One of the recent breakthroughs being the industry's first universal fiber stellar. He has been actively involved in conducting technical workshops with global customers across the Middle East and Africa with the objective to help drive new technologies. Dr. Seldon, I'm very happy to welcome you today and thank you very much for accepting our invitation to present our second webinar. And for all the attendees, please note that if you have any question or any comment, we have time for Q&As after Dr. Seldon finished. And also you can enable the microphone and ask, or you can type in the chat area. So now I will step aside, Dr. Seldon, and give you the full floor.
Great. Thank you, Kolu, for the kind introduction. And also thank Fiber to the Home Council in MENA for giving us this opportunity to share some of the sort of evolution of bend insensitive fiber that we've really seen that is helping to enable our fiber networks to step up and meet the increasing demands that we see coming.
Thank you very much.
So just really quick. It's really all about exponential growth in data. It's the tech ecosystem is disrupting with new use cases. Netflix, YouTube, Facebook. I'm on all those. Twitter, I'm not on there. I guess I'm dating myself. Zoom, everyone is using that. So consumer-led use cases are really driving a lot. My phone keeps telling me my screen time is too high, especially in the current situation. When there really isn't anything else to do outside. But beyond consumers, also enterprise-led use cases. Buzzword Internet of Things. Connected cars, really connected everything, and not just maybe connected like we have today. It's connected in better ways. Lower latency, higher throughput. Really to start getting to a new experience for everyone in some of these applications, and even applications that haven't even been thought of yet. What it all sort of boils down to is increasing demand for data and improved connectivity. And on top of all these things that were happening, now we have our current situation, and it's really a step change. On the left here, we've got some data and then prediction from some European operators really looking at the impact of COVID and lockdown on what's happening with the networks. And so as it's not a surprise to anyone, a huge step change, probably mostly driven by work from home or just the fact that everybody's trapped at home with not anything else to do and need to reach out and connect with folks through the networks. So a huge step change, but they're not predicting that this is going to go back to normal ever, as normal was previously defined. So even maybe a 25% return of folks to work. Yes, there'll be some possible drop in the short-term blip, but they see a new baseline a higher baseline, moving forward, more work from home than traditionally we had been anticipating, and possibly even a higher rate of increase as we move forward in terms of this particular graph is gigabits per day that a person may use versus time as we go into 2023 here. Some of what's driving that, sort of the changes post-COVID to, pre-COVID to post-COVID is obviously a lot of downstream increases, video streaming, conferencing, a huge jump in conferencing. But I think also what really puts a lot of strain on the network, given that the upstream in the network is typically the capability is a lot less than downstream. Huge load on the network due to conferencing, tunneling, social media. It's all just putting new demands on the network, particularly in the upstream. There was a report that sort of summarized the performance of networks. The symmetrical networks that have strong upstream seem to be able to handle this step change in traffic much better than networks that maybe had a much weaker upstream versus downstream. In any case, this is all accelerating the need to upgrade our networks. So on the left here, we've got it's slightly dated now because this has to be redone to factor in COVID. But even before that, a strong increase in when you aggregate all this data together, just a huge amount of data that has to be moved around, and basically doubling in the next few years. Add a COVID step change on top of that, and possibly even a stronger rate of increase, and it's really pushing for investment in the networks. If we look closely at this graph, we've got the fixed internet, a strong driver there, obviously, but even wireless on top of that, the gray bar, really, I think a lot of that driven by 5G is going to drive the need for fiber, in particular 5G with its special latency and high bandwidth requirements. What we also see is that in order to handle this large increase in data, folks are looking at or taking moves to consolidate their networks. So the fixed internet and the 5G or the wireless are really coming together into one network. However you do it, these converged networks are denser, more endpoints, more wireless endpoints through 5G. More endpoints through Internet of Things and some of the other new technologies we discussed earlier. And then with latency and capacity requirements increasing, it's a deep fiberization that we're talking about in these networks. So as we build, expand, or rebuild our networks, let's take a quick look at the fiber considerations, and let's sort of go back and sort of look at like the history, how this thing has evolved so far. So if we look down at the bottom, G652D, that is the original single mode fiber, the standard fiber, the first one developed. So you could put any major optical fiber suppliers' fibers into this table. I just put ours in here just as examples. And so Olight, the basic first fiber, Olight E, slightly improved attenuation in the 1550 and 1310 region, and all at what's a very standard mode field diameter of 9.1 microns. Now, the G652D fibers, I'll just refer to that as D fiber from now on to save a bit of time. It's a great fiber. as long as you don't bend it. And so as networks started to evolve, 15 years ago, the need was seen that we need a better fiber for particular applications. As you get closer to the end of the network, getting into buildings, the D fiber was just not performing well when it had to be bent frequently. Optical loss was too high, and the networks didn't work properly. So the ITU standards body, everyone got together and developed a series of standards, G567, and within that standard, multiple levels of bend optimized fiber performance. A1, the base one, and then A2 with higher bend performance, and then B3 with increased bend performance. Now, at the time, those were all realized with smaller mode field diameters in order to achieve the bend performance. So in sort of comparison, the D fiber easily can be used maybe up to about a 16 millimeter bend radius, whereas the A1 fibers, their sort of design point is a 10 millimeter bend radius. So we're getting smaller and smaller. The A2 fibers design point is 7.5 millimeter bend radius. And then the most bend resistant fiber, 5 millimeter bend radius design point for the B3. The next sort of step in the evolution is back over on the mode field diameter compatibility side, where everything is 9.1 mode field diameter. And so there's a series of fibers. The Sterlite's examples are Olight Nova and Bolite 250. Those are A1 compatible fibers, but they have the same mode field diameter as the original D fiber. And so then, truly backward compatible with D, but giving you the A1 performance. And so we've seen that as networks evolve, more recently, we've seen folks move to more demand for A2 fiber. In particular, for an example, a major European telco moved their entire access network to A2. And that sort of works if you take the whole thing and move it to A2. You're going to have an 8.6 mode field diameter, but that's okay because you change the whole network. You don't have any mode field diameter mismatches, an 8.6 trying to match up to a 9.1. And so that works quite well. And we're seeing more of a trend towards that as well. So the question is, the question marks there, can you have the best of both worlds? Can you now get your A2 bend performance, which is, we'll show, how A2 bend performance can help you in your networks. But the question is, can you also still have true backward compatibility all the way down to your D network? In particular, if you're trying to integrate this with, existing networks. So there was quite a bit in that slide, and but I think I really need to sort of go over the history and sort of set the context of the optical fibers that we're going to be talking about here. So for new networks, they need to perform better. They need to be provisioned faster and cost less. And I'll show you how bend-insensitive fiber plays into this. In the first one, we'll talk about how it allows you to ensure optimal power budget and extend your network lifetime. How it can, in the second one, reduce your total cost of ownership. And then how it can help you create solutions that enable faster network deployment and thus sort of faster getting your customers on board. So we'll start with how bend-insensitive fiber impacts power budget and network lifetime. We'll start with the standard G652D or D fiber, as I will likely refer to it just from force of habit. And as the networks spread, you've got a nice graphic there on the left. You just additional bands as you go deeper and deeper into the network, and also additional bands created by repair and maintenance. Now on the right side, this is providing some performance information on the typical D fiber. It turns out D fiber is particularly poor at handling bends or macro bends, as they're called. The graph here shows loss in dBs versus wavelengths extending past the C band all the way out into the L band. And let's look at the blue curve first. That's the optical loss for one turn at a 10 millimeter radius. And if we take a couple of wavelength points, let's just look at the marked as C band, and close to that is 10 GPON. So the blue curve, it's less than 5 dB, but still that's quite a hefty loss just from a single turn at a 10 millimeter radius, which is not that certainly can happen in network deployments. Just a small increase in the tightness of that band, go down to 7.5 millimeter radius, your loss goes through the roof. So even in the C band, you're talking about 10 dB. If you have a advanced 40G PON, next gen PON system, that you're moving out into the L band out to 1600 nanometers, you're talking about somewhere between 15 and 20 dB loss. And so that the network is not going to work with that kind of optical loss. So bends around 10 millimeter or 17 millimeter radius in a D network are very likely going to cause your network to fail. And so do we really see these kinds of losses, bends in the networks? So let's look at a couple of real life examples, if you will. We conduct this route surveys with a cooperation of a major Indian telco. And we found that even in this particular example is a long distance route. We found that even in that case, there is potential to have bend loss. Now, what we discovered is these were at locations where there had been accidental cuts and associated repair points. And so if we look at the data here, the number of microbends, 4, 2, 3, 3, add up the loss for all those microbends, you're talking about a dB up to 3 dB at 1550. So that's already quite a significant loss. Looking at 1625 up to as high as 6 dB for that worst case link. So sort of in line with the numbers that we had on the last slide, and showing that yes, these kinds of 7.5 millimeter, 10 millimeter radius bends, they do happen in networks, even long haul networks. Likely due to you've got a repair you're doing somewhere. It's not planned. It's likely done in a hurry. It's done under far less than ideal conditions, and possibly without the most trained staff. And so lots of factors go into this, but absolutely we are seeing these kinds of bends and impact on the network out there. What about the access, where you might sort of expect, that's if it's happening in the long haul, for sure it's going to be happening in the access where it's denser and more just variety of the cables and fibers going all over the place. So we evaluated access networks, and we see that they are testing positive for macroband loss. And apologize for that terminology, but anyhow, testing positive nowadays is not a good thing. Also note when you look at the red curves here that the loss increasing with wavelength, that's really a fingerprint telling you that is macro bend loss that's causing these high losses in these links. Now, typically we were able to determine that these were happening in junction boxes and places wherever the fiber is handled. Wherever a human comes in contact with a fiber and has to place fiber and route fiber, that's really where these macro bends were happening. And so let's take a closer look at the network and map out some of these areas. So several factors lead to the loss in the span. And so we can just talk through the feeder distribution and last mile. But let me go down and walk through, starting at the OLT. We got a 10-kilometer fiber link, and these are just sort of average numbers. A joint enclosure, and then continue on, and you've got a power or a splitter also in a joint enclosure. Another about a half a kilometer of fiber cable, and to the second level splitter, and we keep going, and we got let's say 50 meters of so that last drop, and also with some enclosures and connectors, and eventually you get to the ONT. Now let's back up to the feeder. What kind of loss? You're going to have splicing loss, fiber attenuation. Can't get around that. Just the base attenuation. Fiber cuts, connector loss, and I think really it's in that extended 10-kilometer. It's more prone to fiber cuts and then repairs and associated bends associated with those repairs. Once you get into the distribution, obviously, splitter loss, connector loss, splice loss, can't get around those. Here we see a fair bit of accidental bend, as you've got a cable coming in, and you're taking one fiber, splitting it into 8 or 16, and so you're suddenly multiplying the amount of fiber you have to deal with. So those enclosures can be quite quickly quite crowded with optical fiber, really opening up opportunity for accidental bends. And then you get into the last mile, and that's where some of these bend insensitive fibers were originally envisioned to be used. And so if you're using an A2 fiber there, for example, then accidental bends and such will be managed, but that's not always the case. And so there may be some accidental bends. In particular, this may be a part of the network where you go in and you make a lot of adds, moves, and changes, or adding a customer, dropping a customer, reconfiguring that end of the network. And so a lot of touch points there, and just more opportunity for someone to induce a bend in some of these crowded spaces, and cause eventual problems with the network. So we've taken this network, and we've sort of did the math, we mapped it out, did a model, and simulated what the link budget could look like. So starting just with standard D fiber, we took a look at the impact of one accidental bend. And so if we just want to follow through GPON, if we go across fiber attenuation 2.11 dB, nothing you can do about that. Splice loss of a dB, pretty typical. Again, not a lot you can do about it. It's very standard. Some additional connectors, splitter losses, 20 dB in this example. Now the thing that is sort of the variable here that is the accidental bends. It's the most variable thing that we found in these systems. So for example, if you have a 10 millimeter accidental bend with a D fiber, you're talking about a half a dB. But if you have a tight 7.5 millimeter bend, you're talking about 3.755 dB or something on that order. And it's, in that case, in this particular example, it's enough to put you over the edge, and your GPON network will shut down. Now, how accidental bend, how can you get there either through a cut, let's say we mentioned in the feeder, or even just going into one of these splitter boxes and adding fibers, doing splice, doing repairs, and just ending up with one single tight bend that eats up the link budget very quickly and puts your network out of business. The next line, NG-PON, does have a higher link budget, but recall that has a long wavelength component, and recall that the bend loss is quite a bit higher at the longer wavelengths. And so here we see it's like over a 6 dB impact if you happen to get down to a 7.5 millimeter bend. And so that also, even though you have a high link, budget, 32 dB for NG-PON, you'll still put your network out of commission. So in summary, one tight bend can cause link failure when you're dealing with the D fiber. And NG-PON, even though with a higher link budget, it can still go out due to the longer wavelength of operation. All right, so if we take this network and we replace it like magic with a bend insensitive fiber, A2 in this example, life is a lot better, right? Because now if you look at the green box, instead of 3 dB, you got a half a dB. And so your link budget still closes, your network still works. Likewise, in the NG-PON line, instead of 6 dB, you got 1 dB loss. And so your link still works. And so the point is, if we control macro bend loss, then we can really extend the life of the network, even in the presence of all the other losses. Right? So let's move on to how bend insensitive fiber can reduce the total cost of ownership of your network. So sort of carrying on from what we just talked about in terms of the improved resistance to bends, caused by going in, repairing the network, fixing a cut, or even just going and do move adds and drops, modifications to the network. Every time you go in and touch that network, there's a potential to introduce bends. The bend insensitive fiber is much more resilient to that. So we've got a couple of bars here, one for low attenuation fiber on the left, one for low attenuation and low macro bend sensitive fiber on the right. And we're stacking up splitter losses in blue, fiber attenuation in orange, connector and splice losses in gray, and macro bend losses in yellow, I guess it is. And then you have your power budget, 28 dB in this example. And so for the D fiber, the one on the left, you've only got maybe 6 or 7 repairs that you can sort of handle before your network is really not repairable anymore. You're going to have to rip out some of these sections and replace it completely with new in order to get it to work again. On the other hand, if you have a macro bend tolerant fiber, the same stack up, but you see that the macro bend losses, yellow, is really managed very well in this particular case. And then you've got many more repairs that you can implement before you run out of steam in your network. So if you assume that like the number of issues happen in a linear fashion with time, then you can sort of extrapolate that maybe this network will last 3 times longer than the one built with D. And that's obviously going to have a huge impact on total cost of ownership of that network. You can really extend the network, the life of the network substantially. Now, we talked about switching from D to A2, by magic, just wave a wand and suddenly you've got an upgraded fiber plant. So, that's not necessarily real world, but what we did find working with customers that were getting quite frustrated, where they quite often part of the network gets so bad, so many cuts, so many disturbances, they have to go in and replace that section. We did some analysis, and it turned out that for those networks, it does seem to be those specific areas that get hit over and over again and need to be replaced. And turns out, when you go to replace it, if you upgrade it, replace it with an A2 fiber in just that part of the network, you get almost all of the benefit. Sort of under the assumption that it's going to be those areas that come back and get hit again, which seems to be a valid assumption. And so you don't necessarily have to go in and rip out your entire network and replace with A2 to get these benefits. If you, during your normal repair, if you have to go in and replace the part of the network because you can't recover it now, replacing with A2 is highly recommended, as it should enable you to extend the life of your network and get most of the benefit of a full A2 network just by replacing the parts that are problematic. Okay, so move on to the third one. How does a bending-sensitive fiber help you to deploy your network faster? Okay, so it's sort of tied in some respects to what kind of cable it can enable. At least that's one major driver. And so we'll talk about the kinds of cables that are enabled by D fiber versus cables that are enabled by a more advanced fiber like A2. So traditional cables for D have to treat D fiber quite nicely. You've got typical loose tube cable, fairly large tubes, in order to treat the D fiber nice, not put it under any strain, and not in order not to induce any additional loss in that fiber. And so these kind of cables are not necessarily designed or can't really be designed because of the real objective is to treat the D fiber nicely. And then so, ease of use is sort of secondary. So here's some examples. The first one is a 6x6, so 36 optical fiber cable. The next one, 24 tubes, 24 fibers and 6 tubes. And so that would be a 144. So let's look at that one. If we go remove sheath, blue, the next orange, remove the binders, yarns, the next gray, remove buffer tubes, and the final one, clean the fibers. So this would be a traditional gel filled, which is, in general, it's usually required to make a good cable with D. So you're talking about, minutes, the 70 minutes just to get that thing ready to access the fibers on the end. Move over to the last one. That's another 24 fiber per tube, 6 tube optical fiber cable. And again, similar tasks there, but it's it's a 40 minutes to get that prepared. So pretty soon you can spend an entire day dealing with a 144 fiber cable with the kinds of cables that are typically used for D fiber. So what can bending-sensitive fibers do for you? Well, you can enable different cable designs, and you can stop optimizing the cable to treat the fiber nice, and actually optimize the cable to make it more user-friendly and easier to use and quicker to terminate. So one example is a micro-module cable, and typically, in order for this cable to work, you do have to use a bending-sensitive fiber, either A1 minimum or preferably A2. And it's not so much the macro bend characteristics of the bending-sensitive fiber that enables this. Bending-sensitive fibers also have excellent micro bend capability. So microbend is when you put pressure on a fiber, you induce very, very small bends in the fiber, not large, not the macro 180, 360 degree bends, but just very, very slight bends. Those all add up and can cause optical loss, especially in D fiber. D fiber is very sensitive to microbends. The bend insensitive fibers, A1 in particular, A2, are quite bend insensitive, so you can pack a lot of those fibers in a small space. You can squeeze them down. And so in this particular cable example, they're put into a low smoke, zero halogen, a nice soft tube. And so the prep time for these cables is significantly less. The tubes are pretty much, you can remove them by hand. You don't even need to use a tube. Just grab the tube, rip it off. And so it's quite a nice cable. It's a cable designed for quick preparation. And that applies to both the end access time and also to the mid-span access time. You're talking about twice as fast compared to a traditional cable. And that becomes more and more important as you move to higher and higher fiber counts. The amount of time saved can be substantial as you go from 144 to 288 to 432 to 864. If you can do something in less than an hour versus a few hours, or even more than a day, it really starts to add up and helps to accelerate your deployment schedule. So another example that impacts not only just your speed of deployment, which is the one that we're focusing on in this section. I could have easily put this example in the total cost of ownership area. And so this is another type of fiber cable design that is, again, enabled by bend insensitive fiber. So we start with the A example here, which is a typical loose tube design where the optical fibers could be D and are treated quite nicely. It's a large cable. It has to be large in order for D to work properly. Move to bend insensitive, you can shrink that cable down and add more fiber. In this particular case, we've got 57% less area, so it's a smaller cable. And at the same time, we're able to integrate 4 times more fiber. We take it one more step further, throw in a more advanced fiber, a 200 micron diameter fiber versus the standard 250. Bend insensitive fiber also helps to enable 200 micron fiber to work well. You can bump it down to, again, another 36% smaller cable, and then another 1.5x increase in fiber. So throwing these two things at it, bend insensitive and smaller fiber to start with, a large shrinkage in the size of the cable, and at the same time, 6 times more fiber. And so it's just some examples here. So how does that save you money? So as networks are evolving and converging and more and more fiber into, which in many cases is the same space, you can avoid civils, digging and installing new ducts. You can take a cable like A, you can pull it out, you can blow in a cable like B, and you've got 4 times more fiber in the same space. And so it really enables you to make use of existing infrastructure that you already have simply by upgrading to higher density cables. In general, you can easily get 4 times as much fiber into the same space with bend by applying just bend insensitive fiber in your cables. So huge impact on the cost if you don't have to do civils and install new ducts, and likewise huge impact on the deployment time, because you're not doing that work either, which is going to be extremely time consuming, just getting permits and this kind of stuff to dig again and all that. So that can make a major impact on time and cost. All right, so just to recap, we've talked about how bend insensitive fiber helps with all three of these. And life is not perfect. There is one little ointment or bug in the ointment, or if you will, which might need to be dealt with. And that's the mode field mismatch. So if you recall that slide on the optical fiber standards, on the left side, it was all 9.1, completely backward compatible. On the right side, it was all, varying mode field diameter, which helped folks create these A1s and A2s and B3s. So particular example, if you have a legacy network, your mode field diameter is likely 9.1 microns. A typical A2 is either 8.8 or 8.6 microns. So there is definitely a mode field mismatch between those fibers. And so what does this do to you? Even though with the proper splice recipe in your fusion splicer, you melt these fibers together, the A2 and the D, and that sort of somewhat matches these cores together, if you will, flows them together, and you can achieve low splice loss between these fibers. So that's not really the issue. The issue is when you come to try to determine that splice loss. The preferred method, which is a single-ended OTDR, you plug an OTDR into your fiber, fire it all the way down to the end of your link, and get a result, and hopefully it passes, and you can move on to your next job. That doesn't work when you have a switch from A2 to D somewhere along your network, and I'll explain sort of how that works. Now, another method, optical power loss, does work, but that requires you to be in two places at once. You got to be at one end of the network with a calibrated laser source, and you got to be at the other end of the network with a calibrated power meter. And then you sort of have to synchronize and plug into the same fiber at the same time, and then do that measurement. And you're also going to be hoping that your equipment, your laser source and your power meter are properly calibrated. Otherwise, you're going to get an error or slot. You're going to get a number that is an error. In addition, if you do have a problem in your network, the optical power loss measurement is not going to tell you where that is. And so that's another problem. Okay, so going back to the OTDR, why can't you just hook up an OTDR and fire your network and get an answer? Well, the issue is when you go through a D to A2 or A2 to D connection, the way the fiber responds to the OTDR is different. Basically, the D fiber, the signal received at an OTDR from D fiber is weaker than the signal received at an OTDR from an A2 fiber. So, for example, if we go through, let's see, so we've got power loss here at a splice point. I'm looking at the graph. The blue shaded area, that's really where you want to be when you measure. You want to have a value, definitely less than a 0.1 dB, maybe less than 0.05 dB will be desirable. But what happens is when you measure, let's look at the blue curve here. So we're launching in A2, and then we're going into a D/A1. Even if you have basically zero loss or a small loss within this blue shaded rectangle, you're going to measure 0.26, 0.3, 0.2, somewhere in there dB. And you're going to think that you need to go back and break that splice and redo that splice and fix that network. The reason you're getting a loss here is because when you transition from the A2 to the D reports a lower signal than the A2 fiber, and the OTDR thinks that it hit a loss at that splice, and it's not real. If you turn it around, go to the other end of the network and fire it backwards, you're going to measure something along the orange curve, where you're going from D with a low signal to A2 with a high signal, and actually, this is loss. We're negative loss, negative loss, 2 negatives is a positive. So again, you're creating light at that splice. No, that doesn't make sense. Now, if you subtract these two numbers, the blue curve and the orange curve, then you get the real answer. But that requires a double-ended OTDR. It requires aligning traces. It's quite problematic. And so technicians really are confused by this, and it's really difficult to implement this double-ended OTDR successfully. And so it's problematic. And just really quick, we talked about a splice. Similar problem with connectors. And it's even somewhat more complicated because the actual loss of a connector, if you pair up A2 fiber with a D fiber, if you're going, in this case, you're going from the A2 fiber to the D, you can measure a loss. You'll have an optical loss. If you go from D on the right into the A2 on the left, you can sort of almost, conceptually understand, you've got light traveling in that larger core. When it hits that smaller core, you can understand that some of that light is going to be lost. So actually, this kind of a splice or a connection in a connector where you don't have that fusion splice smoothing things out, you've got an abrupt transition here. The loss actually can vary depending on which way the light is traveling. And so again, something like this, where you have a mode field diameter mismatch across a connector, you would also like to avoid that. And so can we have it all? Can we have one product that, brings it all together? And so we went to our fiber development team and said, hey, we want it all. We want the best features of D, our Nova fiber, and we also want the best features of our A2 fiber or our a Bolide E fiber, and said we want these specs, but we also want these specs all at the same time. And it turns out they were able to come up with a unique design that's able to do this. It's not only just the design; it's also built on many years of making A2 fiber and new process evolutions and new process techniques and control. And so quite a bit goes into being able to create this new fiber. But the sort of what it does, and maybe I'll move on to the next slide here, because I think it's a good summary of, it takes us back to the beginning. And so it sort of fills this gap. It gives us an A2 fiber, but it's on the left-hand side here where it is the same mode field diameter. So it, no kidding, has true backward compatibility to the D fibers, and actually all of the D fibers there. Even the Nova, the D/A1s is completely compatible with those, all the way around down to the very basic OH light optical fiber. And so our recommendation is, this is really the fiber for the future. In particular, if you already have networks, then this will integrate and perfect backward compatibility with those networks, increasing your deployment time and reducing issues in link qualification, etc. So just a couple of quick words about Sterlite or STL. Our customer segments cover telcos, cloud companies, citizen networks, and large enterprises. We really focus on end-to-end solutions. I mostly focus on the first one, the optical connectivity area. We also deploy fiber. We get into even some of the actives, FTTX access networks, software, virtualized access products. So pretty much anything you need for your network, there's a good chance that we can help you with that. And just real quickly on Sterlite and numbers, our revenue, 7 global production facilities, innovation centers, really building up our patents, very proud of our zero waste to landfill for 3 of our facilities here in India, first in India, and really worldwide, 30 nationalities, 3,100 employees, and you can see the map there. We're all over the place. And so with that, I want to leave a little bit of time here for questions. You want to hit this thing here. If you want to send us some feedback directly, you can hit these codes, and I'll turn it back to see if we have some questions.
Sure. Thank you, Dr. Seldon, for this very informative webinar. I would like to ask all the attendees if they have any questions. There's questions and answers mode on the right side, and you can enable your mic if you want to ask something, or you just type it in the chat area. So I will give the attendees just minutes. Just if we have any question. Well, apparently, Dr. Seldon, there is no more questions, or there is no questions so far. So at the end, I can only thank Dr. Seldon for this informative webinar and also for his time. And we hope all the attendees enjoyed it and learned as much as I did. Thank you very much, Dr. Seldon. And we are looking to welcome you all on our 3rd webinar next week on the 25th of June, talking about the convergence of FTTH and 5G network with Mr. Samuel Lehman, also from Sterlite. Just 1 minute, Dr. Seldon. So is the standard recommends the switching from 567 to 652? This is a question from Babo.
So I think the question was, is it recommended to switch from G652D to 657 A1 or A2?
Sorry, Dr. Seldon. He corrected the question. He said, sorry, is it recommended to switch from 652 to 657?
Yes. So a lot of folks have already switched to 657 A1. That's a pretty standard fiber that's deployed in many cases around the world. And the main reason was for a little bit better bin loss than over the 652D. And then hopefully through this presentation, I've given you some evidence that actually it may be time to think now to even upgrade that, switch from D fiber all the way to even from A1 fiber up to A2 fiber, based on the benefits that it can give you in terms of total cost of your network, lifetime of your network, the cables that you are able to deploy in terms of smaller cables, higher fiber count in sort of your same duct space, cables which are optimized and easier to work with, speeding up your deployment, networks which are more resilient to cuts and repairs. So I think there's with networks becoming becoming more crowded, there are plenty of options or reasons to take a serious look at upgrading to at least an A2 fiber. And then if you're going to do that, I think you might want to take a look at a truly backward compatible fiber, which has the same mode field diameter as D, so for easy integration into your networks, but also has the A2 capability. And I'd like to also add that yes, Sterlite has this product, Stellar, as I've mentioned, and we were anticipating that this was going to be sort of the next wave, as just like from D to A1 was the first wave of upgrade of the networks, to the fiber in the networks. We're anticipating the next one would be A1 to A2. And actually just today, one of our competitors on the optical fiber side has announced that they also have a similar fiber to Stellar. Has the D mode field diameter and the A2 performance. So I really think that this is validating this idea that this fiber is, I think it's going to be the next sort of universal fiber, can be used anywhere in the network, mitigating bend loss, mitigating micro bend. So I think we're on the right track here.
Okay. Dr. Seldon, we have another question from Mr. Kamel. What is the difference between ITU-TG 652D and ANSI TIA 568.3D standards for fiber?
All right. I have to confess, I am not too familiar with the 568.3D, but I'm certainly there are folks at Sterlite who do understand that standard. So if we could get contact info, I'll get that question answered. It's just not something that I'm aware of right off the top of my head.
Okay, and we have another question from Shiam. Networks with existing G652D and expanding it further with G657A2, is it recommended?
Yeah, absolutely. Putting new fiber in the ground, you definitely want to think about doing that once, right? And putting in, the best solution that that you can afford, that will hopefully give you a much more resilient network in the future. And so, again, the only caution there is that connection between D and A2. And then coming back again to the new solution that Sterlite has put out there. And one of our competitors has a similar solution now, which is the fiber that looks like D, but also it has the bend insensitivity of A2. So that takes away really the only negative in combining these fibers in the network, by making the cores the same. It takes that away. And there's really, it removes a major roadblock, I would say, for mixing these fibers together.
So we still have some attendees are typing, so I will give them a couple of minutes also to take more questions.
Perfect.
So he is asking that if you get the answer, send it to my email, please. This is Mr. Kamel.
Perfect. Yep.
So can we share the slides, Dr. Seldon?
Yes.
With the attendees. Thank you very much for this. And we are waiting for Mr. Muhammad also. I guess he has a question. I just want to ask the attendees that they can enable the microphones. Maybe it will help us more to save some time, if it's okay. Yeah, so many attendees, they are asking for a copy from the slide presentation.
Mm-hmm.
We will share it with them all as Dr. Seldon. Yeah. So we have a question from Mr. Muhammad. What if we mix fibers same type but different suppliers, especially bending insensitive fibers?
So in general, let's say they're all bend insensitive fibers, then in general, everyone's A2 is about the same mode field diameter. Everyone's A1 is about the same mode field diameter. And so as long as the mode field diameters match, then you can do that easily without any link qualification issues or mode field mismatch issues. So yes, you can. You just have to pay attention at the mode field diameters. That's all.
Okay, perfect. So I guess that's it, Dr. Seldon. I'm really so thankful for your time and for this informative webinar. We will share all the slides with our attendees. And sorry, we have also one question. Somebody is typing. I'm sorry, Dr. Seldon, I keep on ending, but no. How much variance is accepted in MFD?
Right, that's a great question. And so, the specifications, it varies by supplier a little bit, but it's typically, the full range is plus or minus, let's say, 0.4 microns. But if you really look at the distributions, they're quite tight because, folks will optimize their processes to really narrow in on that, that nominal spec. And basically at the extremes have, zero incidences of optical fiber at those extremes of the spec. So it's quite a narrow distribution in around the nominal mode field diameter for any kind of quality optical fiber supplier.
Okay, thank you. So we have Mr. James also has a question. Can you share the webinar video with all participants? Definitely, we will send all the participants a recorded, a link with a recorded video for the webinar, and we will share the slides with everybody. So thank you very much, Dr. Seldon. We hope to welcome you all next week with Mr. Samuel Liman, and I wish everybody happy weekend for all the people who is in the Middle East, and a good day, a good rest of the day for the others. Thank you very much, Dr. Seldon.
And thanks, Fiber to the Home Council, Mina, for allowing us this opportunity. Really appreciate it.
And definitely we want to thank Sterlite and Dr. Seldon for accepting our invitation to present this webinar with us. And I want to thank also all the attendees. So I guess some people still are, so everybody is thanking you, Dr. Seldon. There is no more questions.
Appreciate it, appreciate it.
All right, thank you very much.
Okay, bye everybody.
Bye.